Assalamualaikum warahmatullahi wabarakatuh. I am FYP binti Amran, and in this video, I will be presenting on my final year project entitled A Review on CVD Growth of 2D Semiconductors Atomic Layers, Transition Metal Dichalcogenides, TMDs, and its structural properties. I am being supervised by my supervisor, Dr. Nubaizara binti Muhammad. So without further ado, I will begin my presentation. First and foremost, I would like to briefly explain on the introduction of background TMDs. Here, I put a comparison between the TMDs and a well-known nanomaterial in current days, which is graphene. A little bit history on graphene is, it is first studied theoretically by P.R. Wallace in 1947, while Andrei Grimm, along with his colleague, Kostya Novoselov, was the first one who synthesized the graphene. Okay, graphene, due to its zero band gap, it is a good conductor like a metal. But due to this lack of band gap, it limits application when some electronic devices are fabricated, such as when the devices are needed to start and stop the flow of electrons. TMDs overcome this limitation as it has tunable band gap as one of its special features. The tunable band gap are ranging from 1 to 2 electron volt from bulk to monolayer form. And this tunable band gap is significant for a high on-off ratio in electronic device. So here in video 1.1, it shows the animation on tunable band gap from bulk to monolayer form. And some other additional information is figure 1.1, graphene and related structures, where graphene is a carbon nanomaterials tightly packed in honeycomb structure. And in figure 1.2, it shows the zero band gap graphene as mentioned just now. And in figure 1.3, it shows the TMDs and related structures, where the H, R, and T are denoted as hexagonal, rhombohedral, and tetragonal, while the number 1, 2, and 3 are assigned according to its layers number. Now, we move to the background of CVD growth. Here, we will learn on why CVD growth are more preferred compared to other methods. Okay, in general, there are two ways of fabrication techniques, consist of top-down and bottom-up method. CVD growth are categorized under the bottom-up method. Top-down method have its own limitation, where it has poor control over sample thickness and size, making them unsuitable for industrialization. For example, for solution processing, such as the liquid phase exfoliation, the crystal size produced are much smaller compared to CVD. And as for the mechanical exfoliation, it does not produce large surface coverage. But on the other hand, for bottom-up method, particularly on CVD, it can yield greater surface coverage, it can create uniform TMDs, and it also can produce control layers of 2D materials. Moving on to the problem statement. Although graphene has demonstrated as an outstanding material, its lack of band gap still limits its application when electronic devices are fabricated. Since then, there has been a significant amount of study on 2D materials, where one of them is TMDs. Due to their extraordinary properties, TMDs have become one of the most demanded 2D materials in recent years. This development has led to a variety of potential applications. To manufacture atomically thin layers of high-grade 2D material, researchers have studied on various types of synthesis techniques. In this particular part, CVD is one of the most excellent synthesis techniques for producing significant 2D material. The objective of this study are to review the ways on synthesized TMDs layer using CVD growth method and its structural properties. The research question of these topics consists of three, where the first one is how to synthesize TMDs layer from CVD growth method and how many types of them. Secondly is why does a CVD growth method are more preferred to synthesize 2D materials compared to others? And thirdly, what are the distinct differences in structural properties of TMDs using CVD growth method? Okay, why does this study is significant? First and foremost, vapor phase-based direct growth is one of the most dependable and adaptable methods of synthesis for deposition of high-quality 2D materials. CVD is the first notable and successful techniques to produce high-quality and large-area 2D films with scalable and controllable alternative. While for TMDs material already acquire electrical and optical characteristics, allowing them to be exploited in a variety of fundamental research studies and for novel nanoscale application capabilities. And TMDs also is one of the excellent 2D layer materials having a band gap. Now, we move on to the second part of this review, where it consists of TMDs and CVD growth. So, first, I would like to briefly explain on the basic chemical vapor deposition setup in order to understand the mechanism much better. So, as we can see here, there are 6 processes in total. Let's go through on the process A first. So, at process A, the reactant gas or mass are transferred into the tube. And then in process B, the diffusion of precursors or gas diffusion occurred. And then in process C, the adsorption of the precursors onto the substrate occurred. And then in the process D, here in the animation, we can see that the gas-phase reaction occurred and producing intermediate reactants and byproducts. And then moving on to the process E, we can see the heterogeneous reaction or surface diffusion occurred. And last but not least is the process F, where the desorption of the byproduct or mass transport out into the general pump exhaust. So that is the general information on the basic chemical vapor deposition setup. Now, we move on to the part 3, which is the analysis and interpretation. So here we can see the comparison of 4 types of CVD method, which consists of thermal CVD, metal organic CVD, atmospheric pressure CVD, and also atomic layer deposition. So first, thermal CVD. The advantages of this kind of CVD is it can grow large area of monolayer TMDs, but it is difficult to achieve uniform and continuous growth with this CVD. And then MOCVD is an excellent way to control the layers number and grow large areas and uniform films. But the precursors used in MOCVD tend to be highly toxic. And therefore atmospheric pressure CVD is cheaper and simpler setup, as we can see in the schematic here. And it can also produce films with larger grains that are better for electronic properties. But this kind of APCVD are not suitable at growing large area films compared to others. And last but not least is ALD, where it can produce large area and layer controlled growth of various TMDs. But the growth tends to be quite slow and it demands very expensive equipment. Now we move on to the controllable growth for TMDs material. So there are 3 major types that are significant, which are first, large area uniform, second, large single crystal, and third, layer number. So first, large area uniform enables the design of larger gaps between electrodes and addition of more components for integrated optoelectronic circuits. Ways to grow the large area uniform film is by using self-limited growth as proposed by Wang et al. In figure 3.2, we can see the optical image of large area single crystalline obtained by Wang et al. And then moving on to the second part, which is the large single crystal. By growing this large single crystal, we can produce TMDs with high quality. So how we can grow this large single crystal is by reducing the density of nucleation. So in figure 3.3 is one of the optical image obtained for the largest single crystal TMDs domain. And then for the third one is the layer numbers. In general, 2D TMDs exhibit layer-dependent characteristics. For example, monolayer MOS2 displays higher photoluminescence emission, while bilayer MOS2 are more suitable for transistors, logic device, and sensors. So here is some application of TMDs ranging from the biosensors, electronic device, photonic device, piezoelectric device, gas sensors, and also energy storage. So as a conclusion, TMDs material synthesis via CVD are nowadays extensively researched due to its large area, single layer, and excellent quality. However, despite there are numerous published research, controlling growth of wide range of TMDs with desired layer numbers, large domain size, target orientations, and morphologies still remains a challenge. Therefore, the studies on unique structural properties of TMDs need to be continued extensively in order to make them beneficial to the development of future technologies. But in comparison to the size of CVD single crystallography, CVD TMDs are still too small. So more research must be put into discovering new methods for raising the growth rate or lowering the nucleation density. And for application of TMDs are also still in their early years because many built devices have yet maximized the potential of TMDs. Therefore, further research needs to be done on the synthesis and application of TMDs. So that's all from me. Thank you. Have a nice day and Assalamualaikum warahmatullahi wabarakatuh.